Imagine planning a future on Mars, only to discover its unpredictable orbit could derail everything. While Earth spins predictably around the Sun, Mars dances to a completely different beat. What makes its celestial path so bizarrely unique, and how does this cosmic quirk threaten our dreams of becoming an interplanetary species? Let's dive into the cosmic dance of the red planet. Think of Earth's orbit as a nearly perfect circle. It's stable, predictable, and gives us relatively mild seasons. Now picture Mars's orbit. It's not a circle, it's a stretched-out oval, what scientists call an elliptical orbit. This isn't just a minor detail. It's a fundamental difference that changes everything. Because its path is so stretched, Mars experiences dramatic swings in its distance from the Sun. At its closest point, called perihelion, it gets a much more intense dose of solar energy. But when it swings out to its farthest point, aphelion, it's plunged into a deeper cold, much farther from the Sun's warmth than Earth ever gets. To make things even more complex, Mars has a significant tilt on its axis, much like Earth's, which gives it seasons. But when this tilt combines with its eccentric orbit, the effects are magnified in ways we don't see at home. This wobble means different parts of Mars get blasted by the Sun at different points in its orbit, creating a dynamic and volatile climate system. So why does this matter? It's not just a number on an astronomer's chart. This unique orbit has profound consequences for the planet itself. The seasonal extremes on Mars are wild. When Mars is closest to the Sun during its southern hemisphere's summer, the increased heat can trigger massive, planet-engulfing dust storms. These aren't just little dust devils. We're talking about storms that can blot out the Sun for weeks, covering the entire Martian surface. Conversely, the extreme cold when it's far from the Sun helps grow its polar ice caps, which are a mix of water ice and frozen carbon dioxide, or dry ice. These orbital shifts also play havoc with Mars' already thin atmosphere. As the planet gets closer to the Sun and warms up, some of that frozen carbon dioxide turns back into gas, temporarily thickening the atmosphere. When it moves away, the atmosphere thins out again as the gas freezes back onto the poles. This constant cycle of atmospheric thinning and thickening is unlike anything on Earth. And then there's the temperature. Earth has a relatively stable temperature range thanks to our circular orbit and thick atmosphere. Mars? Not so much. Its orbital characteristics create temperature fluctuations that are off the charts. It can be relatively mild at the equator during the day, but then plummet to incredibly frigid temperatures at night. These swings are amplified by its orbit, making for an environment that is incredibly harsh and challenging to predict. Now let's think about what this means for us. Getting to Mars is a monumental challenge, and its orbit is a huge part of that. The key concept here is the synodic period. This is the time it takes for Earth and Mars to be in the right positions relative to each other for a spacecraft to travel between them. Because they're on different orbital paths and moving at different speeds, this alignment only happens about once every 26 months. We don't fly straight to Mars. We launch into an orbit that will intercept Mars where it's going to be months later. It's like throwing a football to a running receiver, but on a cosmic scale. Everything, the fuel, the trajectory, the mission duration, is dictated by this orbital alignment. And if you think getting there is hard, planning a return journey is even more complex. Astronauts can't just finish their mission and head home. They have to wait on Mars for the planets to align again for a fuel-efficient return trip. This could mean a stay of over a year on the Martian surface, just waiting for the right orbital mechanics. These orbital obstacles create major colonization conundrums. Let's start with resources. Any Martian colony would depend on solar power, but the power generated would vary dramatically depending on where Mars is in its orbit. At its farthest point from the Sun, solar panels would be significantly less effective. And those planet-wide dust storms. They can block out sunlight for weeks, potentially causing a catastrophic power failure for a fledgling colony. Managing power, water, and heating and cooling systems in an environment with such predictable unpredictability is a massive engineering challenge. Then there's the habitat itself. We'd need to build structures that can withstand these extreme variations. They'd have to endure intense solar radiation when Mars is close to the Sun and survive the deep freeze when it's far away. They'd need to be sealed against dust storms and handle the pressure changes from the fluctuating atmosphere. We're not just building a house, we're building a fortress against an entire planet's mood swings, all driven by its orbit. And perhaps most importantly, there are the human health risks. The journey to Mars exposes astronauts to high levels of cosmic radiation. Because of the orbital constraints, these journeys are long. And once on the surface, Mars's thin atmosphere and weak magnetic field offer little protection. The amount of radiation exposure would even change depending on where Mars is in its orbit. Protecting human health from this constant bombardment, both in transit and on the surface, is a critical hurdle that its unique orbit makes even more difficult to overcome. But the lessons we learn from Mars' orbit extend far beyond the red planet itself. By studying its unique dynamics, we gain incredible insights into exoplanets, planets orbiting other stars. Many exoplanets discovered so far have highly eccentric orbits, just like Mars, or even more extreme. This ongoing research is also refining our approach to future interstellar travel. Every mission to Mars teaches us more about navigating these complex orbital mechanics. We learn how to better predict launch windows, how to design more resilient spacecraft, and how to plan for long-duration missions in deep space. The challenges posed by Mars's orbit are forcing us to become smarter, more efficient, and more innovative explorers. And it leaves us with an enduring mystery. Mars' orbit is unique in our inner solar system, but what other strange orbital dynamics are waiting to be discovered farther out? What quirks do the moons of Jupiter or the distant objects in the Kuiper Belt hold? Each celestial body has its own story, its own dance, and Mars teaches us that the path an object takes through space is just as important as the object itself. Its wobbly, stretched-out journey around the Sun is a constant reminder of the beautiful, complex, and sometimes frustrating clockwork of our solar system. Thank you so much for watching. If you found this cosmic journey as fascinating as I did, don't forget to hit that like button and subscribe for more adventures into the universe. Let me know in the comments what other space mysteries you'd like us to explore. See you next time, and until then, keep looking up.